Hi. Okay, so today we're going to talk about coping with NP hardness, and it's very appropriate to have Nate talk about the project because the project is about coping with NP hardness. So Nate, the floor is all yours.
All right, so hi, I'm Nate. I'm one of the project TAs. So as you all know at this point, there's a project in this class. We give you an NP hard problem that we came up with, and we ask you firstly to create inputs to it, and secondly, to create solvers for it. So to actually solve the problem on the inputs that everybody else came up with. And we run it like a competition where you try to create inputs that are as hard as possible, and you try to solve as many of the inputs as you can. There's kind of a competitive aspect to it. We'll have a leaderboard during the solver phase for who's doing the best in terms of their solver. The spec with all the deadlines and everything and all of the problem and everything in it is on Piazza. You can look at that. It's one of the pinned posts. But what I wanted to do is just mention the problem, say what it is or the basic idea of what it is and what you're going to be doing. So the problem is you have a bunch of students. You want to put them into a number of Zoom breakout rooms. And between any two students, if they're put in the same breakout room, that contributes a certain amount of stress to the room overall. And it also contributes a certain amount of happiness to the room overall. And the total stress in any room has to be under a certain amount based on how many rooms there are. So we've given you something like a graph packing problem where you want to organize all these vertices, put them into these different bins such that within any bin, the sum of the edges among all the nodes in that bin is not too large, except that there are two weights to every edge. One of those weights is stress, one of those weights is happiness. And so you want to make sure that the sum of the stresses of all the edges is not too large while maximizing the sum of the happinesses. So that's the problem that we've given you. There are a bunch of different ways that you could think about solving it. We have developed a couple ourselves, which we're not going to tell you about. But there are essentially three phases to this project. Phase 0 is just forming a team. We're allowing you to work in teams of up to 4 people. The deadline for that is tonight. So there's a Piazza post. You can look at that Piazza post and just fill out the form with your email and the email of the other people on your team so that we can form the teams and have that ready for Gradescope submission of later phases. The second phase of the project, or phase 1 of the project, is due a week from today. And that is the inputs. So with your team, which you have formed by the end of today, you create inputs to the problem. A part of your grade, 1 out of the 5 points for the project overall, is actually going to be hardness of your inputs. So you give us inputs to this problem, and in phase 2, other people will solve them. When you give us the inputs, you also give us your outputs. It's like the ground truth output. It doesn't have to be optimal, but it should be close to optimal because it will be used to determine the hardness of your output. If other solvers are not able to come close to your optimal output, again, it doesn't have to be optimal, but to your output that you generated for the problem that you created, then we know that it's hard if other solvers are not able to approach it. If other solvers are able to approach it, we know it's an easier instance. So we'll grade you on the hardness of your instance in part. And then as soon as we can, after we get all the inputs, a week from today, we'll release all of the inputs. And you will have until the Monday of Dead Week to work on solvers, try as many different approaches as you feel like, and solve all of the inputs. It probably, we've tested this problem. It's pretty hard. It probably will not be possible to solve all the inputs exactly. So you should consider how you can create approximation algorithms and things like that. And Abhishek will today go over how you cope with an NP-hard problem, how you solve an NP-hard problem given that you can't solve it exactly. That's all I wanted to say about the project, except that there's a slight difference from previous semesters, and that in a lot of previous semesters, we haven't asked you to provide a solution. Sometimes we do, sometimes we don't, but we're in this semester, since we're using it to sort of test hardness of the problem, it's more important that your solution to that your problem be hard and that your solution be good. And those are kind of in conflict. But if you think about it, creating hard problems to which you already know the answer is done all the time, because that's what cryptography is. So that may be a useful thing to think about, and that you could just create problems which you believe are hard and then run your solver on them for a very long time. That's fine. After all, everybody else will not have quite so much time to run their solvers because they will have to run their solver on every input, not just a few. But perhaps a better way of doing it is to create an input to which you already know the answer. Structure the input in such a way that you can put an answer into it which you know, but which will be hard to find. And that's part of why we like the first phase of the project, is that should be an interesting process.
Okay, maybe it's good also to have some questions if somebody else some questions. Because, yeah, thanks Nate for the great explanation.
Thank you for letting me come and mention that. So just as a final reminder, the project team formation deadline is tonight. So make sure you get that Google form in.
Yeah, so feel free to raise your hand or unmute yourself if you have a question. There was one question about the range, the size of the inputs. It's very well defined in the project description. I think it's like 10, 20, and 50 students, right?
Yes.
So is there a resource talking about how to make inputs hard? Well, there is, but it's sort of in disguise, right? So if you think about it, how do you prove that some problem is hard, right? So you do a reduction, right? So that's maybe a hint towards how you can generate hard instances.
Generating hard inputs to which you already know the answer is a different matter, but yeah. I don't know if there's anything in the textbook about it. But
I don't think so, because it's sort of a different flavor. It's a little bit like, as you said, like cryptography and.
Yes, and I'll say that it turns out that most inputs to a lot of NP-hard problems are hard inputs. And so you shouldn't have to work especially hard to make your inputs difficult. Most of the inputs that you come up with are, in a certain sense, are going to be pretty difficult.
Yeah.
Random inputs are already difficult, for instance, usually.
Yeah. And it would be useful to, to take a close look at chapters, 8 and 9. I mean, probably more about chapter 9, coping with NP hardness. We would cover some of it today, but maybe not all of it. And maybe some, some bits and pieces in the book would give you some ideas that would be helpful. Okay, great. Thanks, Nate. And I think I'll now maybe teach them how to solve the project. Let's see if this helps. Yeah. Right. So. Right, so this is sort of like the fourth and last lecture about intractability, complexity. We started with talking about reductions, and we talked about P and NP, and then we got to this interesting concept of NP completeness, and we saw a bunch of problems that are NP complete, and we proved it via reductions between one problem to another. So now let's get back to the real world. Let's say that you're trying to design some algorithm. You want to solve some problem A. Well, you could be lucky, and it could be that the problem that you're trying to solve is a polynomial time algorithm. Either directly, maybe you just argue about the problem directly. You do some greedy algorithm or some DP, or maybe you can solve the problem by reducing it to shortest path or strongly connected component, FFT, max flow, linear programming. Once you write it as one of these problems, you know how to solve it based on the knowledge that you acquired in this course. But in many cases, the problem that you're trying to solve is NP hard. And you can try to prove that it's NP hard by, after not being able to find a solution, maybe you're suspecting that this problem is NP hard because you saw a bunch of problems that are NP hard, like free sat, independent set, would rather cycle, integer linear programming. And maybe you can prove that your problem A is also hard by reducing some NP complete problems to your problem, right? Showing that it is at least as hard as let's say free sat. Okay, so now you're happy. You have a good explanation or a good excuse why you didn't solve the problem, right? Solving this problem would prove that P equals NP. This is like a very hard problem that's worth at least $1 million. So, okay, so now you have an excuse, but what to do next? Is it the end of the story? Right, so if we look at this picture, so we had we are lucky if the problem is in P, and we are not so lucky if the problem is NP complete. Maybe we are sort of in some kind of limbo where we don't know if it's in P or it's NP complete. For example, there are some problems like factoring, where we don't believe that they are NP complete, but we don't know of any polynomial time algorithm. So this is then your situation is more complicated, and you don't necessarily know how hard your problem is. Okay, so the point is that proving that a problem is NP hard is not the end of the story. There are like most problems that are computational problems are NP hard. There are like thousands or if not millions of natural problems that are NP hard. But people in the industry are solving them all the time on real inputs. And the question is how to do that, right? So what to do next? So I had something like there's one answer that is maybe a funny one, is that you could have like 5 stages to how to cope with NP hardness. You have denial, and then you have anger, and then negotiation. Maybe in the end you have acceptance. So I'm not going to go over these things. These are like the 5 stages of grief. But it's sort of similar. Like also here, you're unhappy because you cannot really solve the problem on all inputs in the worst case. So you have to do something, right? So maybe negotiation is the best analogy. So one thing that you can try to do is, you can maybe change the problem. Okay, so you started with trying to solve some problem A, but maybe, the problem A turns out to be NP hard. So maybe it suffices to solve some other problem A prime that is related to it. Okay. For example, you could argue that problem A is NP hard, but this is just because of the reduction that created very obscure, weird instances. And maybe on typical instances, or the instances that you care about, the problem becomes easy. So maybe you can try to capture what you know more about the input. Maybe, for example, you're trying to look at satisfiability, and the formulas are not, general CNF formula, but they are like Horn formulas, right? So there's like a chapter that we skipped talking about Horn-SAT, and Horn-SAT can be solved in polynomial time. So maybe if you have some structure, so maybe notice some structure that makes the problem easy. Okay, so this is, if you're lucky, this is what you'll have, what you'll face. But in other cases, even though you have some structure the problem is still hard. For example, let's say that I want to solve independent set on a graph. You can say, well, I don't care about, this complicated graph with a lot of edges. Maybe my graph is sort of like I can draw it in the plane, and, all the edges don't intersect, right? So these are called like planar graphs. Well, it turns out that solving independent set on planar graphs is NP-hard as well. So maybe this structure doesn't help you. For example, in FreeSAT, you can say, well, maybe the only difficulty in FreeSAT is that maybe one variable appears, in many, many clauses. But then in the homework, you showed that even if every variable appears at most 3 times in every, has 3 occurrences, this problem is still NP-hard. So sometimes even with, with more structure, you can still show that the problem is NP-hard. So it's not always the case that you could make it easier. Sometimes it does help. Okay, so Hornsat is easy. TwoSat is easy. TwoSat is a problem where you have 2 variables per clause. But on the other hand, FreeSat with bounded occurrence or bounded, let's say bounded occurrence, this is hard. So sometimes structure doesn't give you easiness. Okay. So now we go to negotiation, right? So what can you do? Okay, so you really want to change the problem, not only say that the problem is more structure, but you actually want to change what you're solving. So you can use correct but inefficient algorithms. So maybe you're saying, okay, I cannot solve it in polynomial time. This problem is probably not in P, or at least I don't know how to solve it in polynomial time, but maybe I can solve it in slightly more than polynomial time. Maybe I can solve it in time which is almost polynomial. Maybe I can solve it better than exponential. Maybe I can solve it better than brute force. So these type of techniques are called sometimes backtracking, which I'm sure you've seen in previous classes, and maybe you've also seen branch and bound, which is sort of like a more fancy version of backtracking, where you, instead of having Boolean variables, you have, I guess you have a way to estimate like a lower bound and an upper bound on the solution of the remaining problem. So that's branch and bound. We're not going to go too much into that. Maybe I'll mention a little bit about backtracking. So here you really, you instead of saying, the best thing would be that I could solve it always in polynomial time on every input and get the optimal solution. So one way to relax it is to say, well, I want to solve it always correctly, but maybe the running time would be not polynomial time. So that's the first compromise. The second compromise, which is completely different, right, is to say, I insist on polynomial time. So polytime algorithms. But relax correctness. What do I mean by that? So it depends, on the context, but if we are talking about optimization problem, then it makes sense that we would be happy with. Okay. I don't know what happened.
Looks like it might have been lagging or frozen. That's what.
Yeah, I was logged off.
Oh.
So do you want me to go back a little bit? I mean, I don't know for how long it was frozen.
It was just frozen for those last 2 bullet points, I think.
Okay, so the first thing is backtracking to do something inefficient but correct, maybe something that runs slightly better than brute force. And the second approach is to use what's called approximation algorithms. These are efficient algorithms, but they don't necessarily give you the optimal solution. you settle for near optimal solutions. Okay, and we would focus on this second bullet today. Okay, and this is what's called approximation algorithms. So for example, let's say that you want to, find the best, the shortest tour that a traveling salesperson can do to visit N cities. Well, maybe you are okay with finding a tour that, is not the best, but maybe, at most twice the best. Maybe you have some slack in your budget. So in some situations, this is possible. In others, actually, it's still hard, even if we relax the optimality to be near optimal. Okay, and we will talk about that today. Other approaches would be to find heuristics. And this is a big topic, and we would not really go into much depth here. But in general, once you find heuristic, you can perform some kind of local search or some kind of guided search that benefits from these heuristics to find optimal solutions faster than brute force. These algorithms work very well when, they work even in polynomial time in some cases, where we don't have more than one local minima or one local maxima. But for many NP-hard problems, we have, a bunch of them, and therefore we need to somehow handle this problem. And I'm going to talk about it very briefly in the end. And maybe the most useful strategy, and I also urge you to try this strategy for handling the project, is to reduce the problem, right? So you got some weird problem about, Zoom rooms that nobody thought of before this year. But there are some problems that people have thought of for like 50 years, like SAT or traveling salesperson or integer linear programming, right? So you can reduce your new problem to a well-studied problem. Now, this other problem would be usually, because by definition it would be NP complete, but it could be an NP complete problem that was well studied, and then you can use solvers, off-the-shelf solvers for this known problem. So for example, if you can write your problem as some kind of SAT instance, then you can just use a SAT solver. If you write it as some kind of integer linear programming, you formulate it as an integer linear programming, then you can run any package that solves integer linear programming problems, right? So that's a very useful technique. And notice that it's very important which reduction you're using. You can apply several reductions from your problem to, let's say, SAT, but some of them would be easier than others, right? We know that SAT cannot be solved on all inputs in polynomial time. So maybe SAT solvers work particularly well on some inputs, but not on other inputs. So you need to do some kind of trial and error and see, maybe one formulation of it as a SAT problem is easier than the other. So that's maybe the most useful trick. There's another approach, which is called fixed parameter tractability. This is, again, you want to solve the problem, correctly. And the one thing that you notice is that the problem has some inherent parameters in it. For example, let's say in vertex cover, we want to find a subset of vertices that cover all the edges, right? So if I tell you, I'm looking for like 10 vertices that cover all the edges, then apparently you can find whether there exists, 10 vertices that cover everything or not. You can find it in time pretty efficient. And the reason that you could do it is because this number 10 is rather small. So this is sort of like algorithms that are efficient provided that some parameter is small. I can give you another example. If you recall, we talked about the problem of independent sets. Independent sets in general graphs, this is an NP-complete problem, but independent sets on trees is an easy problem. You can solve it using dynamic programming. It even appears in the book. We haven't covered it, but there's a natural dynamic programming algorithm for finding an independent set in a tree, okay? Now, in general graph, it's NP-complete, but what if you have like a tree and I give you a tree with an additional edge? Can you solve it on this graph? Well, yes, you can, because you can sort of figure out what to do with this edge. Once you figure this out and you remove this edge, then you get a tree and you can run independent set on the remaining graph, right? So you can run dynamic programming on the remaining graph. So if like I give you some graph which has like a tree plus a few additional edges, then you can actually solve it fast in the parameter, which is the number of additional edges. Okay, so maybe you would start to be exponential in this number, but if this number is a constant, then this is still okay. All right, so these were like, you know, very, from a bird's eye view, we talked about all these methods, and now we're gonna dive deeper and see a few examples for each one of them. Okay. Yeah, and if you want to look it up, I mean, this is not really covered in the book. So if you want to look it up in Wikipedia, this is called FPT. All right. So let's look at the first example, which is backtracking. Backtracking is, again, we want to solve the problem correctly, and we want to do it slightly better than brute force. And a very famous algorithm, a SAT solver algorithm called DPLL, it's the initials of the people that invented this algorithm. This algorithm is doing some kind of sophisticated backtracking on a CNF formula. It's trying to, you know, what are you trying to do? You're trying to say whether there is a satisfying assignment to the formula or not. So the most naive thing would be just to go over all possible assignments, check if they satisfy the formula. If yes, then good. If no, then answers that this is unsatisfiable, right? And this would take us like to go over all 2 to the n possibilities and evaluate the formula. Now, if we look at the formula, we can sort of do some kind of tricks. It's sort of similar to how you solve a Sudoku. Like you start realizing, well, this variable doesn't have more than one option, so I have to assign it to this value. And this, you know, other variable, now that I assign this variable, now I can also determine the value of another one. And maybe at some point you're stuck and you cannot really deduce the value of any variable. So then you just, you know, try both, you know, 2 options and you backtrack. So let's see the DPLL algorithm. So you get some formula, CNF formula phi. Well, the first thing that you check, you check maybe one of these clauses is already empty. An empty clause just means that, you know, there's no variables inside it, so you cannot satisfy it. So if you have an empty clause, then this is unsatisfiable. The other, you know, extreme case is where you are left with no more clauses, right? So you just, the formula is nothing. And by default, we're saying that the empty formula is satisfiable. Okay, so then you return true. Okay, so these are just, you know, 2 edge cases. Okay, so now you look at the formula. It's sort of like a formula like the one that I wrote above. And you look if there's a variable that appears only positively. Okay, I actually forgot here something. So if there's a variable, let's say in this formula, look at a variable. So you look at x, it appears both as x and x naught. Y appears both as y as y naught. Z appears both as z as z naught. But w appears only as w. So if you see such a variable, you know that it is safe to assign this variable the value true, right? There's no reason to assign this variable the value false because it would not help you satisfy any of the clauses. It only appears positively, so any satisfying assignment, you know, it could be that there are satisfying assignments that assign this value, this variable w, the value 0, but then you can change it, right? You can change the value to 1 and it would not hurt you. It's sort of similar to the exchange argument that we had, right? So any satisfying assignment could be changed so that the value of w is 1. So in this case, we just set the value of this variable to 1, and we sort of simplify the formula. So every place that this variable appears, now the clause is satisfied. And every place that it doesn't appear, I'm not doing anything. Okay, so this is, I'm doing some kind of simplification and I'm doing recursion. If a variable appears only negatively, then I'm assigning it 0. Okay. Another important step is that if a clause contains only one literal, then set the variable such that the literal is satisfied and recurse. Okay. So what do I mean by that? So let's say that I have another variables. I don't know, like let's call it, I don't know, Q. And let's say that I also have this clause that involves only Q. So in order to satisfy this formula, I must satisfy this clause that involves Q. So I must set Q to 1. So if I see only one variable, I know which value to assign to this variable, right? Because I want to satisfy the entire formula. Okay, so all these things are sort of things that I have to do to satisfy the formula. Or you know, the first two are sort of like, I don't lose anything by doing that. So these are sort of like easy decisions, right? If I'm in one of these 3 cases, then I have a very easy decision. But maybe I'm not in any of these 3 cases. And in such a case, I'm just going to pick one variable. I don't tell you how. So this is really, you know, this is really the name of the game, how to pick the good variable v. And then I'm going to recurse on the two options. I'm going to assign this variable 1 and simplify the formula and run dpll on this simplified formula. And on the other branch, I'm going to assign it 0 and I'm going to run dpll on the simplified formula. Okay. So let's see what dpll would do on this formula. So first we identify that there is this variable q. So we must set q to 1. So I'm going to pick q equals 1 here. Okay. And now I look at, you know, now I look at what's remaining. Okay, so I set q to 1. So this clause is satisfied. And I see that w appears only positively. So now I'm going to, you know, assign w. And I'm going to assign it to 1. What do I get by that? So this clause is dropped, this clause is dropped, and this clause is dropped, right? All these clauses are dropped because w was set to 1. And now I have these 2 clauses. I see that x is only appears positively, so I fix x to 1. And then, you know, this drops this thing. And then I see that y appears only positively, so I fix y to 1. And I get a satisfying assignment. Okay, so this was like a simple case. I didn't have any branches, like I had only one branch, one path. But in general, sometimes I'm going to get stuck and maybe I have, I don't know, like A or B. And B naught or C or C naught or A naught, something like that. And then I cannot apply any of the rules that have only one child. And in this case, I would need to pick one of these variables and look at the two branches. Okay, so in some cases, I will actually split, right? And in general, we expect this algorithm to not work in polynomial time. So in the worst case, it would take something that is close to exponential time, but on some interesting real life application, this algorithm works pretty well. And the name of the game again is how to pick a variable if you're not in one of these three cases, right? So this is really a crucial point. And one strategy is maybe to pick the variable that appears the most, because this would simplify the most clauses once you assign it. Okay. All right. So this was backtracking. It's usually something that is sort of easy to program, but very hard to argue about the running time of this thing. So in the worst case, yeah, obviously this cannot run more than 2 to the n time, but how much time it takes on real life CNFs, it's not very clear. I guess you can test it and see if it works. Okay, so this was about backtracking. There's also this technique of branch and bound, which is sort of for non-Boolean case, where you want to somehow look at the remaining formula and look at the remaining subproblem and give some kind of lower bound and upper bound on it. And if you realize that solving this subproblem would not give you something better than what you already know, then you can sort of cut this branch in the tree. Okay. All right. So the next thing that I want to talk is about approximation algorithms. This is yes.
Is it okay if we stop really quickly for some questions about the DPLL backtracking?
Yes.
I'd rather give a couple from the chat.
Yeah.
Emilio, did you want to ask? Okay. We just have a few quick questions about the definitions, making sure that people understood the recursive call. Sorry.
Yeah.
Notifications are going off. The recursive call where you're setting v equal to 1 or equal to 0,
yeah.
and then maybe a quick clarifying statement on the bullet point that says if a clause contains only one literal, then set v such that the literal is satisfied, and then where you were going after that.
You just recurse. I mean, I have no, I was running out of space, but you just recurse after you assign this variable. So like in both these three options, let's give them some numbers, okay? So in 3, 4, or 5, we are sort of making a decision about some variable. And we're making one decision about it. And once we fix the value of this variable, either by 3, 4, or 5, we can simplify the formula. So let's, okay, so let's say, so if the formula is like the formula that we started with, okay, it will be hard to start with the formula that we started with. So let's say that the formula is, I don't know, W or X or Y, and X naught or Y. Let's say this is the formula. So what do I mean by assigning the variable and simplifying? So let's say that I assign the variable W to 1. What would happen? What would the formula look like after I'm doing this assignment? I'm looking at it clause by clause. The first clause is satisfied, right? W is set to 1, so I don't care about X and Y. It's 1 or something. 1 or something is 1, so it's satisfied, so I can just drop this clause. So this clause is dropped. The second clause, I didn't touch it because I only assigned W. So this clause remains the same. And the third clause, notice what happened here. I assigned W to 1, but I took not of W. So this is like 0 or Z. And 0 or Z could be simplified further to just Z. Okay, so when I'm assigning the variable W, I'm sort of deleting it from the formula. Some of the clauses would become satisfied. Some of the clauses would become shorter, and some would be unchanged. So you can see that sort of like after you assign a few variables, the formula is starting to look easier to solve, right? So that's the point of this algorithm, that you know, even if initially it looks a little bit hard, after you assign a few variables, and the formula becomes sort of easy. And then, you know, if I want to now look at this new formula and say, is it satisfied? Well, surely it is, right? It's a very simple formula, so I can see how to satisfy it.
And how would you characterize this approach in terms of the categories that you listed out at the beginning of the lecture, with the fixed parameters versus being okay with an inefficient runtime?
This is the inefficient, correct, but inefficient.
Okay.
And in the worst case, this would take like exponential time. Sometimes it can take. Sometimes there are like very beautiful, sophisticated analysis that show that it runs slightly better than 2 to the n, maybe I don't know, to the 0.9 times n or something. But you know, we don't know of any algorithm for SAT, for example, that runs in time, I don't know, 2 to the square root n, for example. So all these algorithms, we have no guarantees how well they work. But they work pretty well in practice.
Okay.
Right.
I think that's it for now. Thank you. Sorry about that.
No problem. I'm happy to answer questions. All right, so the next thing, and hopefully I will get to dive a little bit deeper here, is about approximation algorithms. You can take an entire course about approximation algorithms, and there's a beautiful book by Vijay Vazirani. The name might sound familiar. And what is an approximation algorithm? This is how we talked about 2 ways to relax the question. So one was to relax the running time, and the other was to relax like the optimality or like the correctness, right? So the general setting is that you are trying to solve some optimization problem, some minimization problem. So you have some problem A, and you want to find an optimal solution that minimizes some objective function. Okay, so this might seem a little bit abstract, but actually you can see that there are a lot of examples that we already talked about, like vertex cover or set cover, or, okay, we haven't talked about TSP, traveling salesperson, but we will talk about it probably later today. So these are problems where you want to find something which is minimal, right? Also shortest path is an example like that, but for shortest path, we know how to solve it optimally, right? So these are problems that we want to minimize something. We don't know how to do it optimally. It's sort of NP hard, right? If we can do it optimally, then we show that P equals NP. But we want to relax it a little bit. So what do we want to say? So given some instance i's, given some input I, let's define opt I to be the value of the optimal solution. Like the solution that you would have if you run over all possibilities and took the one that minimizes the objective function. Okay, so this is like the ideal solution. And on the other hand, there's the solution that your algorithm produces. Let's call it algae, or actually the value of the solution that your algorithms provides. And your algorithm is called an approximation algorithm with approximation ratio alpha if on any instance, the value of the algorithm is at most alpha times the optimal value. Okay, so in particular, okay, so we can also add another inequality. So the value of the algorithm cannot be better than the optimal solution, right? Because the optimal solution, like the algorithm produces some solution. So really what we get is that the value of the algorithm is somewhere in the middle between opt and alpha times opt. Okay, and maybe that's enough for you. Maybe you don't care about getting the best one, but you care about getting the best one up to a slack of alpha, right? So maybe there's like a vertex cover that uses 100 vertices, but you're okay with getting a vertex cover with 150 vertices. So maybe your algorithm can provide you with something like that. Okay, so we actually saw an approximation algorithm earlier in this class. When we talked about greedy algorithms, we saw an approximation algorithm for the set cover problem. And set cover turns out to be an NP hard NP-complete problem. There's a very simple reduction from vertex cover to set cover. Perhaps you've seen it in the discussion or in the homework. I believe it appeared somewhere there. And if not, then I recommend looking at the reduction in the book. And on the other hand, we saw some greedy algorithm that worked not so badly on set covers, right? What we showed is that if the best solution is you can use k sets, then the algorithm produces k times ln n sets, right, that cover all the elements. So this is indeed an approximation algorithm with factor alpha, which is ln n plus 1. Okay, so this is an algorithm with approximation ratio alpha. Okay, so I just wanted to remind you that, and you can go back to this lecture about set cover and look at this argument again. So this was a perfect example of an approximation algorithm that works efficiently, right? So the algorithm that we described, the greedy algorithm, works in polynomial time. All right, and now let's talk about vertex cover. A subset of vertices S is called a vertex cover of a graph G if this subset S touches all the edges in the graph, right? And here's an example. So I drew a graph, and the vertices marked in orange, they touch all the edges, right? You can check it for yourself. And the problem that we want to solve, the optimization problem, is to find the minimal size set that is a vertex cover, right? The minimal vertex cover. And last lecture, we talked about why vertex cover is NP-complete. There's a very simple reduction from independent set to vertex cover. Independent set is NP-complete, so therefore also vertex cover is NP-complete. Okay, so again, we are facing some, we want to optimize some problem. We know that it's NP hard to get the best solution. But what we'll show now is that you can get an approximation algorithm for that. For vertex cover. Before I show you this approximation for vertex cover, I just want to mention, because vertex cover can be thought as a special case of set cover, by these greedy algorithms that we saw earlier in the class, you already get an approximation algorithm for vertex cover. So the set cover algorithm also gives an approximation algorithm for vertex cover with alpha that is ln n plus 1. But what we'll show is that for vertex cover, we can get something much better. For vertex cover, we can get an approximation ratio, which is only 2. Okay, so it doesn't grow with n in particular, and it's a very nice small constant, right? Okay. So next is that we'll show approximation algorithm with alpha equals 2. All right. So the idea is to leverage the connection between vertex cover and matchings. Okay, so let me recall what a matching is. A matching M is a subset of the edges of the graph such that every 2 edges in the matching do not share a vertex, right? So let me show you an example here. What would be a matching? So this is an edge. This is another edge that doesn't touch it. And this is the third edge that doesn't touch it. Can I find the 4th edge that doesn't touch all these others? What do you think? I mean, I don't have much options. The only one that I didn't touch are E and H are not connected, so I cannot find more edges. Okay, so how I'm going to use the connection between matchings. The question is how to use matchings in order to solve the problem of vertex cover. Okay, And notice that I'm not going to solve it optimally, but I want to get some kind of an approximation. Okay, so the idea is sort of similar to what I did in this picture, to find a maximal matching in the graph. By maximal, I mean that you cannot add another edge to it, cannot be extended. Okay, so this is not the same as maximum, which is talking about the matching with most edges. I just want a max matching that I cannot add to it another edge. And that would be enough. How can you find such a matching efficiently? I want to see if anybody has an idea how to find a matching that cannot be extended. You are encouraged to raise your hand and suggest how to do that. Yes, easy.
I'm not sure if this is going to make sense, but just a greedy algorithm to keep choosing an edge when possible. And after you choose an edge, you can delete the vertices and the edges that touch those vertices.
Perfect. Yeah. So a greedy approach would work, right? So, and in fact, this is like sort of what I did here in this drawing, right? You sort of every time you want to pick an edge, just look if there exists like one edge that doesn't touch the existing edges in the matching. If such an edge exists, add it to the matching. If not, then stop, right? You found the maximum matching, right? So you just add edges to M greedily while you can. What does it mean while you can? As long as there exists an edge E in E that doesn't touch M. Right. So, and I mean, if you look at the picture, it's very clear what you do. Like you pick an edge, then you pick another edge that doesn't touch it, then you pick another edge that doesn't touch these two, and so on and so forth until you cannot pick any more edges, right? This gives you a matching. And of course, this algorithm runs in polynomial time, right? So there's nothing too fancy about that. In fact, there is a sophisticated algorithm that finds the maximum matching in a graph, but this is sort of out of scope for this class. It was one of the first polynomial time algorithms. It was developed in the 60s by, I believe, by Edmonds. It's quite a sophisticated algorithm. Okay. So what's the connection between matchings and vertex covers, right? So let's look at these three edges in the graph. What can you tell me about any vertex cover? So if I have this matching that contains these three edges, we know that every vertex cover must cover all the edges in the graph. So in particular, it must cover these three orange edges. So the vertex cover must cover at least either one of A or B, one of C or D, and one of G or F. So it must choose one in each of these pairs. So the size of the vertex cover should be at least the size of the matching. Or in other words, if M is a matching and S is a vertex cover, then the size of M is at most the size of S, or the size of S is at least the size of M. And the proof is simple, right? So S should at least cover the edges in M. But to do that, every edge in M, right? If I look at some pair UV that is an edge in M, we must have that either U is in S or V is in S, right? I need to cover this edge. I must have that at least one of these vertices should be in the set. Maybe two of them are in the set. And notice that these pairs are disjoint of one another. So this means that we must have at least m vertices in S. Okay. So that's a lower bound on the size of the vertex cover, but notice that I didn't solve the problem, right? I just told you some connection between vertex cover and matchings, and I gave you some lower bound on the best vertex cover, right? So if you give me a maximal matching in the graph, this is a lower bound on the vertex cover. But notice that a matching is not a vertex cover, right? It's a collection of edges, not a collection of vertices. So the question is, how can we use this claim to get now a vertex cover that is not so bad? So we want to find now a collection of vertices that forms a vertex cover, and such that the size of the set is not much bigger than the optimal solution. And the idea is to just take, if you look at the matching, just take all the endpoints of edges in E. So for every edge, I'm just going to include the two vertices that this edge connects. Okay, so in particular, here the subset S tilde would be like A, B, C, D, F, G. Okay, so these 6 vertices. And the claim is that this is a vertex cover on one hand, and on the other, that this is a pretty good vertex cover. It's at most twice the optimal vertex cover. Okay, so let's see first that it's at most twice, like the size of S is at most twice the optimal one. So what's the size of S? It's exactly twice the size of M, where M is some kind of maximal matching. And we know by claim 1 that this is at most 2 times the value of the optimal. Sorry, let's call it opt-G. Like the optimal vertex cover on the graph G. Okay, so we got that the size of S tilde is at most 2 times the optimal value. And we also need to show that S tilde is a vertex cover, right? I mean, it's not, it's not super interesting if I just give you a collection of vertices that is small, but it's not a vertex cover, right? So you need to show me that this set is not only small, but also that it's a vertex cover. And this is kind of simple. How do we show that? So the claim is that S tilde is a vertex cover for G. So how can we show that? Let's assume by contradiction that S tilde is not a vertex cover, right? So what does it tell us? It means that there exists some edge E in the graph such that S tilde doesn't touch E. Right? That's the definition of, vertex cover. If something is not a vertex cover, there must be an edge that is not touched by this set. But notice that then E doesn't touch also the matching M. So, and this is a contradiction to the fact that M was maximal, right? Because in particular, I found an edge in the graph that doesn't touch M. So I can add this edge to the matching and get a bigger matching, right? And this is contradiction to the fact that M was a maximal matching. So this proves that indeed this is a vertex cover. Okay. And if we go backwards to the previous picture, you can just see that these 6 vertices that correspond to the 3 edges indeed cover all the edges. Okay, so let me just show you that. If you look at all the edges in the graph, each one of these edges touches one of these vertices, right? Either this vertex, that one. One of these 6 vertices, they touch all the edges in the graph. Of course, they touch the edges in the matching, but they also touch everything else. And the reason that they touch everything else is that if they wouldn't, then I could extend the matching even further. Okay. So what did I get by all that? I got an algorithm that runs, very efficiently. It just finds the maximal matching and then just take all the endpoints. So it more or less runs in, I don't know, linear time probably, or maybe quadratic time. But anyway, polynomial time. And this algorithm produces a subset of vertices that is a vertex cover and whose size is at most twice the optimal vertex cover. So what does it give us? It gives us an approximation algorithm with ratio 2. Now this seems very simple. Can we improve it? Can we get like 1.99? This turns out to be a very difficult question. So the belief is actually that we cannot do better than 2. Only like 2 years ago, there was a proof that it's NP hard to get an approximation ratio which is square root 2. So like getting like 1.3 would already prove that P equals NP. And there's a very big open question in complexity theory called the unique games conjecture. If you're interested, I recommend Googling it up. That if this conjecture is true, this would imply that it's NP hard to approximate this vertex cover to ratio better than 2, like let's say 1.999. Okay. And there was recent development in these conjectures that leads us to believe that it might be correct. And it's quite an interesting development that happened over the past couple of years. Okay, so I guess this brings us to the next slide, which is about the fact that sometimes even to approximate is hard. And let me show you an example with the traveling salesperson. So I mentioned this problem, I think, several times, but we haven't even defined it so far in the class. So what is a traveling salesperson? So you have a bunch of cities, and between every 2 cities, you have some kind of distance. So let's call it, A, B, C, D. So it's similar to problems on graphs, but you should think of it as if every 2 nodes are connected. Okay, so maybe here the distance is, I don't know, 10 miles. Here it's 20, here it's 30, 12, I don't know. So there are some distances between every 2 cities. Okay, so you're given n cities with pairwise distances. So you have some, distance dij for every I and j between 1 and n. Okay, and your goal is to find the shortest tour. So think of yourself as some kind of traveling salesperson that wants to sell, I don't know, books, and you want to visit all these cities, and you start at Berkeley, and you want to visit all the cities, and you want to minimize the travel time or the travel distance that you have. So what do you want? You want to visit all cities, so you want to find a cycle. And it doesn't make sense to visit one city more than once, so you want a cycle that visit every city exactly once. Okay, so think of pi as some kind of permutation, and you visit, first you start at pi 1, then pi 2, then pi 3, and so on, up till you reach pi n. You want to visit every city once. and you want to minimize the sum of the distances. So the distance between the first city and the second city and the third city, and so on and so forth. Okay. So, right. And I claim that actually for this problem, the traveling salesperson problem, not only is this problem NP complete or NP hard, but it's even hard to approximate it to within any ratio. So no matter which ratio you're aiming for, it's just impossible to approximate it to within this ratio. And we're going to prove, in one shot that this problem is NP hard to compute exactly and also to approximate. And this sort of brings us to this area of hardness of approximation that shows that even if we want to approximate something up to some ratio alpha, sometimes this is an NP complete or NP hard problem. Okay. So the theorem here is that for any constant C, if you can solve TSP, you can have some C approximation algorithm. Sorry. In polynomial time, then P equals NP. Okay, what would be the idea? I want to reduce the problem of Rudrata cycle to an instance of traveling salesperson, and I want the case to be as follows. If there is a Rudrata cycle, then I want the best tour to be of very low cost, and if there is no Rudrata cycle, then I want the best tour to be very expensive. Okay, so how I'm going to do that? I'm starting with a problem on Rudrata cycle. So I'm just getting a graph G, which is unweighted, right? So in Rudrata cycle, I just get a graph, undirected, unweighted, and just ask whether there exists a cycle in this graph that visits every vertex exactly once. Now, can I give this instance to the TSP problem? Not exactly, because in TSP, we really have, every two cities are connected. So I cannot just give TSP a graph for which it's not even clear if there's a cycle or not. So the input to TSP is just a collection of distances between every two cities. So definitely there's some Rudrata cycle inside this graph that I drew up here, because this graph contains all the edges between every pair of vertices, right? So the question is not really about whether there exists a tour, but rather what's the best tour, okay? Okay, so yeah, I guess I want to say that we show a reduction from Rudrata cycle to TSP. Right, so this is this proof. So given this graph, I want to tell you what are the distances now. So for every two vertices, I'm going to set the distance to be 1 if these pair are connected in the original graph. And I'm going to set the distance to be, really large. I would want to set it to infinity if I could, but let's say that I want to set it to some finite number. So I want to set it to C times N. Otherwise, right? If this edge does not exist. Now, what would happen? So I want to consider two cases, right? If G had a Rudrata cycle, so let's call this thing, I don't know, G prime, some kind of graph with distances between every two pairs. So if G is a Rudrata cycle, then the TSP, then G prime has a tour of length N, right? I just can take whatever Rudrata cycle I had on G and I look at the same cycle on G prime, and I notice that all the distances are 1. So when I sum the sum of all the distances, I get that the sum is exactly n, right? But what happens if G doesn't have a Rudrata cycle? Then every cycle that I look in G prime must contain something which was not an edge in G, and therefore it must contain something that has weight C times n. So in that case, the best tour has length which is at least C times n, right? Actually more than that, because this is just one edge and I have more than one edge, but let's just focus on these two cases. So notice that, you know, I took this problem and I sort of did a reduction such that if I was a yes instance, that I got something with TSP of length n, and if I was a no instance, I got a TSP instance with length at least 2 C times n. So I created some gap between these two cases. And now if I know how to approximate with approximation ratio C, then I can tell the difference between these two cases, and therefore I can also solve the Rudrata cycle problem. So, right, so if we could approximate TSP to ratio C on the graph G prime, then we could solve Rudrata cycle exactly on G. And why is that? So let's say that I have some kind of approximation algorithm A. So I'm running some algorithm A on G prime. If the algorithm gives me a solution that has value smaller than C times n, then I return yes. And if it gives me a value that is bigger than C times n, I say no. And notice that I always get the answer right. So let's say here. And why is that? Well, if G was indeed a graph with a Rudrata cycle, then the value, like the optimal solution for G prime would be n. And the algorithm on G prime should give me something that is at most C times n. So I would end up in this case and I would return yes. On the other hand, if the input G was a no instance, it's a graph with no Rudrata cycle, then the optimal solution for G prime would be bigger than C times n. So in particular, the values that the algorithm would return would be even bigger than that, because the algorithm cannot give me something better than the optimal value. So in this case, I would end up here and I would return no. So in both cases, I returned the right answer and I solved the Rudrata cycle. And you know that if I solve the Rudrata cycle in polynomial time, then I prove that P equals NP. So therefore, this completes the proof. So what does it show? It shows that for some problems, like vertex cover, we can approximate it, you know, with a guarantee that we get something, you know, not as bad, not so bad, right? So maybe twice as, you know, maybe we need twice as many vertices as the optimal one. But for other questions like TSP, we cannot even guarantee that we get any constant approximation. In fact, this C could even depend on n. It could be like something like, yeah, sorry, this should be little n here. C could be even like n squared. It could be a function of n, and this reduction would work as well. So there's no function or reasonable function of n for which we have an approximation ratio C. Okay. I want to tell you, you know, that there is one change on this problem that makes it actually, that if we do this change, then we can actually approximate it well. And notice that here, the graph that we created had these very weird distances. We could have like two, you know, we could have like let's say that this was the original graph. Now the distances would be 1, 1, and c times n, right? And this is not really proper distance metrics, right? What we know about distances, like let's say in 3D or 2D, we know that they satisfy the triangle inequality. We know that, you know, if we want to go from here, let's call it A, B, C. If we want to go from B to C, you know, the distance between B to C is at most the distance between B to A and the distance between A to C, at least in any reasonable geometric interpretation of distances. And this sort of is not satisfied in this definition of the problem. So if we relax the question and we demand that the distances themselves satisfies the triangle inequality, then it turns out that there is an approximation algorithm. Actually, there's a bunch of approximation algorithms. So one that is presented in the book has ratio 2. And there's a very classical algorithm by Christofidis. I'm sorry, I'm not sure how to spell this name, but so Christofidis, and I think it's a pretty old approximation algorithm, probably from the 70s, that get an approximation algorithm with ratio that is 1.5. I should say that both these algorithms rely on the fact that you sort of apply some minimum spanning tree on the network, and then you take the minimum spanning tree and you convert it into a tour in some sophisticated way. So actually, algorithms that you already learned are useful in this approximation algorithm. And very recently, this year, a group from University of Washington came up with an approximation algorithm that is the first improvement over this 1.5 algorithm. And the approximation ratio is 1.4999999. There are like 32 nines here, something like that. And it's a very sophisticated algorithm, and they also gave a talk about it in the Fury Lunch. So if you are interested in this topic, I just want to say that this is, you know, there was a major breakthrough in this topic in the last year after like 50 years that people were stuck. So that's quite interesting. And it's not clear what's the best thing. So maybe you can lower this 1.4999 to maybe 1.4. We know that you cannot get to one, like you cannot go below, let's say 1.01. That's NP hard. But the real question is what's best approximation ratio that you can get. Okay. All right, so I see that I am almost out of time. Let me tell you a little bit about local search, and maybe Umesh would tell you a little bit more about that. So the third, maybe the last approach that we will discuss is this hill climbing or local search. That's a quite useful optimization technique. It sort of is inspired by optimizations over continuous spaces where you can actually show some guarantees of this method. But we sort of look at the discrete analog of it. So let's say that we have like a discrete solution space, let's call it X. So think of it as maybe like all possible subset of vertices, and we want to find like the vertex cover. Or maybe think of the solution space as all possible assignments to the variables, and we want to satisfy like a CNF form. Okay, so X is like this exponential sized domain. And let's say that we also have some value function F that gives us for every possible solution some value. And our goal is to maximize this value, to find the solution that gives us maximal value for F. Okay, so you can phrase a lot of the questions that we discussed in this last few weeks. You can express them as some kind of maximization problem over discrete solution space. So the idea of a local search is to find a solution by starting with some random solution. A random solution is usually not such a good solution. In some cases, it's actually an approximation, which is not too bad, but maybe we want something even better than an approximation. And then the idea is to start with, once you start with a random solution X, to start improving the value. So maybe you notice that if you change X slightly, I don't know, you move to the right, then the value of the function increases a bit. So you go to X prime. And then maybe you do another step and you notice that you increase it even further. And you can sort of climb this hill if you think about this. Of course, you need to do everything discretely. And you sort of can improve your situation as long as there's something in your neighborhood, some X prime in your neighborhood for which the value of the function is higher. If such a value exists, then you take it and you make this step. Now, what's the problem with this approach? The problem is that you can, let's say you started here at X, you can get stuck at some local maxima. Okay, and this local maxima is not necessarily the global maxima because, right, so this is better than that. So there are ways to deal with that. So one approach is to just, try again. So let's say that I started with X and I got stuck. I don't know, maybe it's a local maxima, maybe it's a global maxima, I'm not sure. But I can try again. Maybe now I'm sampling another X that is here. And then when I'm doing the local search, maybe I'm getting to a better point. So I can do some kind of, I can do some restarts in using randomization. And this would allow me to, to increase the probability of success, right? Because maybe I have very small probability of hitting the global maxima, but if I repeat it enough times, then maybe in one of these trials, I would get to something in the, in the downhill of this global maxima. And once I get there, then I climb to the top of this hill and I got the best solution. So that's like one approach. Another approach is called simulated annealing. The basic idea there is that you don't only go upwards, in sort of, you should think of it as some kind of process that changes with time. In the beginning, you are very explorative, right? So you want to explore the universe. So you sort of go wherever you want to. So you don't make these checks. But as long, as time goes by, you've seen some stuff already. So now you get a little bit more picky, and now maybe more and more you want to only increase the value. So the idea of simulated annealing is that if this, okay, so let's write what happened in simulated annealing. You have another, let's say, another loop, outer loop. And here, even if the value does not improve the value of F, then with probability, that is somehow, what is it? It's e to the minus the difference between these two things divided by the temperature. With this probability, you would pick X prime. So what's the idea here? Sorry, you assign X to be X prime. So the idea is that, if the difference between these values is quite large, then with very small probability you would take it. But if it's kind of small, then you allow yourself to go there with some non-negligible probability. And there is this temperature here, and the temperature sort of starts very high, you allow yourself to be very permissive and to go and explore as much as possible. But as time goes by, this temperature becomes lower and lower until you're frozen. It's sort of like the temperature is zero, and then you don't really allow any change, any changes that makes the value of the function go down. Okay. Yeah, I'm sorry, this is maybe not the most clear explanation, but you know, it's a good idea to take a look in the book about simulated annealing. It's sort of a very intuitive algorithm, and it's sort of a, you know, modification of local search that allows you to take steps that reduces the value of the function by a bit. Okay, and I guess you need to update the temperature a bit. So the temperature depends on some function of the iteration number. Okay. And there are some intuitions that come from physics, why this is actually something that mimics or simulates processes like in nature. But I guess I don't know enough about that to give you, you know, a lot of depth about it, but perhaps Umesh would have more to say about it in the next meeting. Yeah, I guess so. This covers more the things that I want to say about coping with NP hardness. Yeah, I'd be happy to answer your questions. And since I see that we're running out of time, feel free to leave. And I guess see you on Thursday.